This is a video about bonding of some common ligands that are found in organometallic complexes. I'm showing you here some IR data on some metal carbonyl complexes. The frequency of a carbonyl stretch for free carbonyl is 2,124 inverse centimeters. And below I have a table of some metal carbonyl complexes and their carbonyl frequencies. Notice that these metal complexes are arranged from low frequency to high frequency. And these are, again, the stretches of the CO bond. So that means at the top, we have longer, weaker carbonyl bonds, and towards the bottom, we have shorter, stronger carbonyl bonds. And so this table is arranged in a gradient, basically, of the longest carbonyl bonds to the shortest carbonyl bonds. They are also arranged according to the charge on the metal ions. You'll notice at the top here that we have the metal complex that has most negative charge, and towards the bottom we have the metal complex with the most positive charge. So now I'm going to explain these observations with the fact that the carbonyl ligand is both a sigma bond donor and a pi acceptor. The carbonyl ligand is a weak sigma donor and a strong pi acceptor. And I'm going to draw the sketches of those two interactions with the metal d orbitals. The lone pair electrons on the carbon of this carbonyl are in an sp hybridized orbital, and they can donate into one of the metal d orbitals of similar symmetry. Here's an example. In this way, the carbon is forming a sigma bond with the metal d orbital, and it's also a sigma donor. The carbonyl ligand also has a pi star orbital that will interact with the metal ion. In fact, it has two pi star orbitals. I'm only going to draw one of these two. The pi star orbital can interact with one of the metal d orbitals of compatible symmetry. Here's an example of one of those d orbitals. Electrons on the metal can back bond or pi bond to the pi star orbital on the carbonyl ligand. The interaction here is pi back bonding, and the carbonyl ligand is acting as a pi acceptor. Now, how does this explain the IR data that I've written above? At the top of the table are the metal complexes that have more negative charge or more electron density on the metal ion. The more electron density that the metal has, the better it is at pi back bonding. And this pi back bonding is putting electrons into the pi star orbital of the carbonyl, weakening that bond. So the more electron density that's on the metal, the better it is at pi back bonding. Not shown in this data is also the fact that the metal-carbon bond becomes stronger. The metal-carbon bond becomes stronger because the metal is pi bonding to carbon. And at the same time, as the metal pushes electron density onto the carbon, the carbonyl ligand becomes a better sigma donor. This model of bonding can explain the data above. The pi back bonding is an explanation for the trends that you see in this table. And also, the trends that we see in this table are evidence for the existence of pi back bonding in carbonyl ligands. One interesting point about this particular data set is the fact that the iron carbonyl stretch is actually higher frequency than the free carbonyl stretch. How is this possible? How is it possible that iron carbonyl has a higher vibrational frequency or a stronger bond than than a free carbonyl? An argument is that iron is so electron deficient that no back bonding occurs, and rather the carbonyl acts as a pi donor from its HOMO molecular orbital, which is slightly anti-bonding with respect to the carbonyl bond. Now let's move on to another ligand that's typically found in organometallic complexes, and this is dihydrogen. It has very interesting bonding interactions with metals. The bond length of free dihydrogen is 74 picomolar, And the bond length of a metal-coordinated dihydrogen is typically somewhere between 82 and 90 picomolar. We can explain this once again by looking at the molecular orbital interactions of the metal ion d orbitals with the hydrogen bonding and anti-bonding orbitals. A sigma bonding interaction between dihydrogen and a metal ion is through the sigma HOMO between the hydrogens. If I draw the electron cloud looking like this is the sigma HOMO of that dihydrogen molecule. And it can interact in a sigma fashion to a metal d orbital of compatible symmetry. Here is an example. This interaction is a sigma bond, and the dihydrogen is acting as a weak sigma donor to the metal ion. Dihydrogen can also interact with metal ions through pi accepting or pi back bonding. The sigma LUMO of dihydrogen would look something like this, where there is a node between the two hydrogens. This orbital is not filled, it's the LUMO. And so if there is a metal d orbital of compatible symmetry, like this for example, electron density from the metal can back bond onto the dihydrogen LUMO, which is the antibonding orbital. This interaction is pi back bonding, and in this way the dihydrogen is acting as a pi acceptor. Dihydrogen as a pi acceptor might be unexpected, but it explains why dihydrogen bound to a metal ion has a longer bond. It's because the pi back bonding weakens this sigma bond between the hydrogens. If there's enough pi back bonding, the hydrogen-hydrogen bond will actually be weakened enough to break. And this is actually very relevant to catalysis. Depending on whether the H2 molecule is bound in a sigma fashion, as it's shown in this picture, versus a dihydride complex where it's actually acting as two hydrogens that are bound individually to the metal ion, the formula can be written in different ways. For example, in this molybdenum complex, the hydrogen is actually two individual hydrogens bound to the metal ion. This is a dihydride complex. The two hydrogens are actually bound individually as sigma donors with one negative charge each. In the second complex, the dihydrogen is actually bound as a dihydrogen. And this can be shown in the formula. It can also be said in the name, a dihydride versus a dihydrogen. The difference in bonding between these two metal complexes come from the fact that the carbonyl ligands bound to the second complex are strong pi acceptors. These strong pi acceptors compete for the metal electron density. The more pi back bonding that is happening with the carbonyls, the less pi back bonding that can happen onto the dihydrogen. The less pi back bonding onto dihydrogen leaves the hydrogen-hydrogen bond stronger and intact compared to the first case where the dihydrogen has been cleaved into two individual hydride ligands. Now let's talk about phosphine ligands. Just like in the previous case of dihydrogen, you'll find that phosphine ligands have an unexpected pi back bonding ability. Here's an interesting trend in the metal phosphine bond strength. I'm talking about this bond. Trifluorophosphine has the strongest bonds with metal ions in this series, whereas trimethylphosphine has the weakest bonds. This is counterintuitive because you would expect the electron donating substituents on the trimethylphosphine to make the lone pair of electrons on the phosphine ligand better base than in the case over here where we have trifluorophosphine. The electron withdrawing fluorines should make this a weaker base. And in fact, the phosphorus electron density is richer on the right-hand side than it is on the left. And we are increasing basicity from left to right. So, if trimethylphosphine is a better base, why isn't it making a stronger bond with metal ions? The reason for this is because, unlike nitrogen, phosphorus is not as simple as just a donor. The lone pair of electrons on phosphorus can certainly act as a donating ligand by interacting with metal d orbitals of compatible symmetry, like this. In this way, the trialkylphosphine ligand is acting as a sigma donor and forming a sigma bond. There are two explanations for the observed pi back bonding onto trialkylphosphine ligands. I'm going to explain the one that has the most experimental evidence to support it. Imagine the ligand salcs on the phosphorus that match in an antibonding way to a phosphorus p orbital. This is a pi star LUMO on the trialkylphosphine. The metal d orbital of compatible symmetry will interact through pi back bonding with this pi star orbital. It turns out, in fact, that trialkylphosphine ligands are very good pi acceptors. Now, the best evidence to date points to this sigma star back bonding as pictured. However, there are also those who argue that phosphorus can accept electrons into its empty 3d orbitals through an expanded octet. This metal pi back bonding explains the trend above that shows that the most electron-poor phosphines have stronger bonds to the metal ion. It's because they can accept more of the metal electron density onto phosphorus, shortening that phosphorus metal distance. Now, the best evidence to date points to sigma star back bonding as pictured above. However, this is well debated, and there are many people that don't believe that this is the case, but believe more strongly that phosphorus can accept electrons into an empty 3d orbital through an expanded octet. Again, this is under debate, but the best evidence so far points more strongly to the pi star back bonding as pictured. Another interesting ligand that I'd like to talk about is carbenes. You may have briefly seen carbenes in your organic chemistry class. These are neutral electron deficient carbons that only have 6 electrons in their octet. Ethylene can actually be thought of as 2 carbene fragments. This is a useful analogy to think of metal-carbene interactions. This interaction can be explained as a sigma bond from the carbon to the metal and a pi back bonding interaction from the metal to the carbon. Here's a picture of what the sigma bonding interaction might look like. And considering that the carbon itself has an empty p orbital, a pi back bonding interaction might look something like this. In this way, you can think of the carbon making a double bond to the metal ion. 2 of the electrons from that bond are coming from carbon, and 2 of them are coming from the metal ion. Now, there are actually 2 classes of carbenes. The first class is called a Fischer carbene, and this is where the bonding is just as I've described. In a Fischer carbene, it's as if the metal is contributing 2 electrons and the carbon is also contributing 2 electrons. These are characterized by the electrophilicity of carbon. In this particular type of carbene, carbon is electrophilic. In a second class of carbenes, carbon is more nucleophilic. In these, we think of the metal as having a 2+ charge and the carbon having a 2- charge. Both of the electrons from the metal-carbon bond are coming directly from the carbon, or that's how they are behaving anyway. And again, in this case, carbon is more nucleophilic. Depending on the behavior of the carbene, it can be classified as either a Fischer or a Schrock carbene. Now I'd like to talk about some pi bonding interactions through pi systems. I will start with the simplest pi system, which is ethylene. The HOMO on ethylene is a pi bonding molecular orbital, which I could draw something like this. And this orbital can interact in a sigma donating fashion with metal orbitals of compatible symmetry, as shown here in this sketch. In this way, the pi ethylene is acting as a sigma donor and making a sigma bond to the metal ion. Pi ethylene can also act as a pi acceptor. The LUMO on pi ethylene might look something like this. And a metal d orbital of compatible symmetry can donate electron density into this empty LUMO. A sketch of this interaction looks something like this. In this way, the pi ethylene is acting as a pi acceptor, and the metal is pi backbonding into the pi star LUMO. The sigma interaction here is not directional, however, the pi bonding is directional. This type of interaction is supported by evidence that free ethylene bond length is shorter than the bond length when ethylene is bound to a metal ion. For example, the bond length of an ethylene molecule bound to platinum is 137.5 picomolars with a vibrational frequency of 1,516 inverse centimeters. This is a longer, weaker bond than free ethylene, which has a bond length of 133.7 picomolars and a vibrational frequency of 1,623 centimeters. The increased bond length and weaker carbon-carbon bond of the platinum complex is explained through metal pi backbonding. As the metal backbonds into the pi star LUMO of the ethylene, it weakens its carbon-carbon bond. Now let's look at another pi system, the pi allyl ligand. I know you've seen this at least once in organic chemistry, but as a reminder, I'm going to draw the pi molecular orbital diagram for this molecule. Now the pi system here has 3 p orbitals that are contributing, and so I should get 3 pi molecular orbitals in the end. The lowest energy pi molecular orbital has 0 nodes and has bonding interactions between all 3 carbons. The next energy level will actually have 1 node directly through the center carbon. I could actually erase that center p orbital and replace it with a node. And the third highest energy level molecular orbital has 2 nodes, 1 between each carbon. This whole system has a total of 4 electrons. And so this is my HOMO, and this is my LUMO. I'm going to letter these A, B, and C. All 3 of these orbitals can interact with the metal ion. I'm turning the molecular orbital on its side so that one face of this pi system is facing the metal. For molecular orbital A, I'm going to point all of the negative lobes away from the metal and all of the positive lobes towards the metal. Now, this pi system can interact with the metal d orbital of compatible symmetry. For example, a dz squared would work. Remember that there's electron density on the top face and the bottom face of this pi system that can donate into this orbital. This is forming a sigma bond with the pz as pictured, but it could also do this with another orbital of compatible symmetry. For molecular orbital B, I have one of the positive lobes facing the metal ion and one of the negative lobes facing the metal ion. This orbital can interact with the metal orbital of compatible symmetry. For example, a p orbital that's facing in and out of the plane of the paper. Once again, this will form a bond, but this time it is a pi bond. Through pi donation of the electrons from the HOMO. This B orbital is the HOMO, and so the electron density from this pi system on the ligand is donating to the metal ion in forming a pi bond. Now, orbital C does not have any electron density because it is the LUMO. And so the interaction of this orbital with the metal ion is going to be accepting electron density from the metal. Metal orbital of compatible symmetry can donate back into the ligand. And so this is pi back bonding. Please note that the interactions of A and B are both donation from the ligand, while in C, the ligand is acting as a pi acceptor. In this way, the pi allo ligand can act as a sigma donor, a pi donor, and a pi acceptor. The final pi system that I will talk about here is the cyclopentadienyl anion. Once again, it's useful to look at the pi molecular orbital diagram to help us understand what kinds of interactions are possible with the metal ion. In this case, I have 5 p orbitals that will contribute, and so I should expect 5 pi molecular orbitals. The lowest energy orbital has 0 nodes, and so has continuous bonding interaction between the p orbitals of all 5 carbons. There are 2 degenerate orbitals, each having 1 node. The node in the left-hand case is between the 2 orbitals in the front and the 3 orbitals in the back, whereas the node in the right-hand case is actually directly through one of the atoms. There are also 2 degenerate orbitals that have 2 nodes each. Another way to draw these is from the top. So that would be the top view of this orbital. Here's the top view of this orbital, top view of this orbital, top view of this orbital, and the top view of this orbital. So maybe that top view would help you to understand the nodes a little bit better. Each of these orbitals has compatible symmetry with some of the metal valence orbitals. I've written those orbitals in blue here. And before I move on, I'm going to fill up my molecular orbitals with the appropriate number of electrons. I have 6 electrons in this pi system, and so that makes these 2 orbitals my HOMO, and these 2 orbitals are my LUMO. The lowest energy orbital can interact with the dz squared or a pz orbital on the metal ion, and it can donate to that metal d orbital or the p orbital in a sigma bond. In this way, the ligand itself is acting as a sigma donor. The 2 HOMO molecular orbitals can interact with the dxz and dyz orbitals of compatible symmetry. So I've tried to sketch that here. In this way, these 2 orbitals are both interacting in a pi bonding fashion with the d orbitals. Again, these are pi bonds, and therefore the ligands are acting as pi donors. And the 2 LUMO orbitals can interact with the dx squared minus y squared and the dxy, once again in a pi fashion. However, now these ligand orbitals are empty, and so it's the metal that is actually donating into the ligand, and so this is a pi back bonding interaction, and the ligands themselves are acting as pi acceptors.